Coming to our next seminar in the Center for Mathematical Medicine seminar series. Today, our speaker is Dr. James Bannon from University Health Network and Princess Margaret Cancer Center. He's a postdoctoral fellow, I believe, working in the Benjamin Habe Keynes lab over at the Princess Margaret. So, yeah, so very far to travel today. Thank you for commuting all the way over here. And I appreciate you coming over and really looking forward to your talk. Generally, these things are kind of open for questions if you're comfortable with that. Yep. Yep. The only thing we'll ask is that we try to speak into the microphone so that those online can hear us. So thank you so much. Yeah, I'll pass around the microphone. Thank you so much.
I thought I was doing that one.
I thought
I turned it down because I didn't know what the.
Shane didn't give you this.
I can do. I explicitly turned it down because I didn't know what I was expecting. But this is.
I think you should wear this.
That makes sense.
I think it is on now. Pocket.
Can we hear? Can you hear me online?
Karina, can you hear?
Sorry. Yes, I can hear. Sorry. Yes, I do hear. Thank you so much.
Check. That seems to be giving me audio.
Karina, can you hear James speaking? The lapel mic does have a button at the top.
I can hear. Do you hear me?
Make sure that it is set to green. It is set to green.
Yeah, we're on green. I could raise it. Maybe that's me.
No, I think it's close now.
Yeah. Hello? Could it be?
Alrighty, then we should hear. I can hear. Okay.
Okay.
Thank you, Karina.
Thank you so much. Wonderful. That works out very well. I think this talk is scheduled for 2 hours, so I'm not going to take that whole time. I think it said 2:30 on the initial invite, and so no, I was expecting 1:30. I thought 2:30 was going to be. I don't have 2 hours in me. Got it.
Got it.
I think we're okay.
So hearing Karina, just want to make sure that you guys have the audio confirmed.
Okay, great. Right. Thank you.
All right. Are we good to go?
We're
All right. So my talk today is titled "The Topology of Personalized Medicine: Noise, Biomarkers, and Recommendation." I'm going to cover two things, and I'll explain the talk in detail, or I guess 2 bits of research, and then sort of do some. But before that, do some ground setting. So what I do is I work in sort of pharmacogenomics, personalized medicine for cancer care over at the hospital. Before that, for those of you who follow American politics, no relation. A little bit about me. Did a BA in English Lit at Swarthmore. Got a PhD in computer science at NYU, where I did my my doctoral work was on using sort of discrete Ricci curvature on graphs to find biomarkers of response to immunotherapy based on gene expression. Happy to talk about that afterwards. And then sort of in January this year, I came to UHN to work in Ben's lab as a postdoc. And my job has been sort of continuing more on the pharmacogenomic side. So the way this talk is going to go, I'm going to introduce, I guess, sort of show of hands for those of you who's heard the term pharmacogenomics or knows what it means. Wow. Okay, then we'll go through the slides a lot faster. Then I'm going to talk about sort of, I'll define some of it and then get to what it actually takes in practice. What are the realities of the data that we're dealing with? How noisy is it? Why it's a problem, and how it can, and then sort of taking 2 steps. One is the research we've done using a neural network to rank cell lines based on their susceptibility to drug with an explicit awareness of the kind of noise we find in the data. And the second is sort of perspective and sort of initial first stages in using computational topology to sort of look more fine-grained at the rankings we produce. And maybe sort of build sort of specific patient-centered ranking using those tools. So pharmacogenomics, obviously the big goal of cancer care. I guess sort of initial ground stating cancer is bad. We want to get rid of it as much as possible. And so we usually, when we say personalized cancer therapy, we mean finding the right treatment for the patient based on what the particular nature of their disease is. And particular nature often means molecular data, because cancer is a disease of overproliferation of cells. Classic example is, EGFR mutations in lung cancer. Usually depends on which exon, but certain mutations leave you susceptible to therapy with erlotinib. Some make you resistant to it, but that's the basic idea. And this is important because there's tremendous costs if you fail. If you pick the wrong treatment, right, people suffer. They have terrible side effects, spend a lot of money, family goes through hell. I'm sure we all know someone or know someone who knows someone who's been through something like this. And for sort of last down, this is maybe my Americanness showing, the financial outlay of going through that cost, that care, can be tremendous. And at least in some countries, it can bankrupt you. And that's terrible if you are bankrupt and still have the same cancer you started with. So in the ideal case, we'd love to have a patient come in, obtain samples from their tumor, perform some molecular analysis, select a treatment, and either eradicate or control the disease. I say control because I think sort of the modern understanding of cancer care doesn't involve necessarily trying to kill all the tumor cells. If you can make them senescent or stop dividing, then render it a chronic condition so that people die of something else many years later, that's a success. Pharmacogenomics lives in that intersection. So we do the data analysis of taking existing molecular analysis and outputting what do we think would be a good treatment selection for a person based on what we see. Leads to a couple questions. So since it's a math institute, I figured a formal definition is important. Pharmacogenomics is the study of finding the molecular factors that determine treatment response. Usually we're looking for things called biomarkers, like the example from above, EGFR mutations. Alternately, you can look at, so that would be something like a single variable marker. Or in immunotherapy, sometimes the overexpression of PD-L1s would be a single variable marker. But often, we might want to come up with multivariable ones that sort of harmonize, or usually just weighted average several expression or several different molecular measurements at once. And they can be either prognostic, meaning sort of how aggressive is the disease, what's the disease state. So example may be determining the subtype of cancer. That would be a diagnostic or prognostic biomarker. Predictive would be, say, as the name suggests, can you predict something? Can I predict, if someone will respond to this treatment, how long they'll live, et cetera? It's obviously not a clean overlap, right? Because if something is about aggressiveness of disease, I can also predict survival time from that. But it's a good rough categorization. The question is, how are we doing on this front? And the answer is, room for improvement. We have only about out of 26,000 genes, we only have 51 that are associated with FDA-approved anti-cancer drugs, and only around 176 out of God knows how many have associated genes. So finding these is a pretty important problem, and it's sort of something we do every day. And Ben would kill me if I didn't mention this. Clinically measurable is crucial. It's important to find, you'll see a lot of research out there on like single cell genomics or spatial transcriptomics. And those are great, but far too expensive to ever deploy in the clinic for at least another 10, 15 years. So it'd be great to have some things that are actually measurable and can be like done on a patient's relevant timescale before to serve as their biomarkers. Did you have a question? In the back in the blue shirt. The Rockies. I'm looking at you with the Rockies shirt. Yes, you. Did you have a question? I thought I couldn't tell if you were moving or raising your hand. Okay, sorry. So the question becomes, what should we measure? And there's a whole bunch of options. Mutations, copy number, sort of genetic things about the structure of the DNA in the cells. Epigenetic stuff like how coiled is the chromatin, where is it? What's the level of transcriptomics, or what's being expressed in what quantity? Where, if you want to have spatial, and in single cells if you can do that. Proteins, metabolites, and then for our point, drug response. So today's talk is really going to focus on these two for two reasons. One, keeping prerequisites to a minimum. Two, because in the model organisms that we're talking about, transcriptomics seems to be the most effective features. And that's done, that was found by doing a sort of massive multi-institution bake-off of machine learning model building. Where should we measure it? Immortalized cell lines. Everyone familiar with what this is? Yeah, okay. So they're nice in that we can generate a lot of data. We can screen things in parallel. And it's easy to characterize them in terms of multiple omics. So it's just to keep the big database. Only have to look at it once. In ideal case, we have reproducibility, and sort of because they're so simple, right? Because it's just a cell in a petri dish. If you can't predict response to a drug in a cell line, you're extremely unlikely to be able to succeed in patients, because then you have the whole complication of what's the tumor structured like, is the drug even getting there? The pharmacokinetics of everything. And in fact, most biomarkers have been developed in cell lines first. They're done, the way that these are measured usually is through something called a cell line viability screen. The way this works is you take a bunch of drugs and a bunch of cell lines and try them in each one, and then look at which ones have died, where you sort of measure, usually it's sort of fluorescent ATP, which Petri dishes are lighting up still because there's still cellular division and which are not. Look at the ones where there's some or all cells have stopped and try to find characterize those cell lines and say what's changed. What about those makes them susceptible to this drug versus the other ones in the screen? And then ideally, this is the big picture goal is to have a whole big collection of molecular profiles, come up with, based on a nice variety of model organisms, and then construct, drug sensitivity screens, and then be able to say, okay, I can put in the omics and output what I think their drug response is going to be. What's the catch? This all sounds very nice. It seems very pretty. We're in the age of big data. I just told you these things are cost effective. What's the issue? Reality is the issue. There are many screens we've been doing on since the 1990s, which I think some of us in the room remember, myself included. And they've been done across different institutions, different drugs, different cell lines, and under different experimental conditions. So the problem is, this is what we'd want. The AAC is the area above the dose response curve. Higher means cell dies at lower doses, more effective, more sensitive to that compound. So we'd ideally want in either the same experiment or across two experiments, same drug, same cell lines, to be resistant and sensitive, and everything should be nice. Fits a hug. But in reality, what we get are things like this. If you look, this is the Broad CTA Broad screen on the left with an nilotinib compared to a Genentech screen from several years later. Very low correlation. And the same thing is true with the Sanger GDSC squared. So that's fun. And it doesn't necessarily stay bad, but it also doesn't necessarily get better, right? So we have some are very good, like verinostat, but also a broad effect chemotherapy drug like paclitaxel. Kind of not great. So the question becomes, how do we learn? And it gets worse, right? Because this is biological replicates for the same sample. So we have a tremendous amount of noise, and you can say, okay, if I want to predict the drug response, is this even really viable? Is this real or not? How can we possibly say what we're doing is right? And you'll see a lot of terrible, in my opinion, I guess I would say careless machine learning papers that just throw expression and response into a neural net and output it and say we have a Pearson of 0.9. Thank you. Please, accept us to no reps. But that sort of leads you down false avenues, right? So suppose this is like the first replicate. You'd think, okay, A is more resistant than B, and they're both more resistant than C. Cool. But if the assay is noisy, in fact, you're not actually concluding much at all. And these things can be permutable. So the mathy way is you have to be mindful of group assays group actions due to assay noise, I guess. And so you can't really conclude much about the relative ordering. So what's our initial plan? Develop a multivariable machine learning model, aka take the expression, summarize it in some way that explicitly learns to account for the noise and phenotypic measurement. So that takes us to our neural ranking part of the talk. So the idea is to take a neural network, and we want to assign a score to each cell line that indicates how sensitive that cell line is to a given drug. So we're working on a drug basis. And that's important because one, in the research context, setting up, we wanted to clarify in the context of this beginning, we sort of set up with choosing the right treatment for the right patient. Here we're working with a given drug and trying to say, what can we isolate as who's responsive and who's not? Obviously, those problems are pretty much twinned, right? One's for the dual of the other. But it's just worth noting because it's a lot of other papers will pool drugs together, and that's another problem because you sort of could end up just sort of learning to distinguish which drug you're treating as opposed to what's actually going on. So we learn these scores by looking at pairs of inputs. We essentially are, instead of learning an input-output function a la this, we're trying to learn to order the cell lines based on what we see. So we pick a threshold delta, and we only consider pairs valid if their AAC values are separated by a value at least delta. right? So it's sort of a well-separated condition. And below delta, we sort of say these are like relatively noisy, likely subject to permutation. Oh, well, let's not learn it and try and sort of say, we can find, if we can tell, essentially we're sort of making a more coarse-grained approach of saying, can we tell sensitive from resistant from middle of the pack? And that's a more informative thing than saying, can I perfectly predict the response? But the hope is that you will generalize, right? And that ordering it will be better and that you'll get a better correlation because you'll be ignoring noisy phenotypes. So what we're doing is we build a deep neural net to maximize the concordance index. Hence, we call this deep SciNet. And we use what are called twin or dual convergence architectures. So we clone the network twice. We clone it once. So we have two copies of the same network with identical weights. Pass in the input, and then each one produces a score. And then the loss function is saying, given the scores that you've provided me, would I order these compounds correctly? So, more specifically in training, we look at AACs with a difference greater than or equal to delta. Pass in their messenger RNA expression values, measured in terms of log transcripts per million, centered and scaled, all the fun stuff. And we get a score QA and QB, which we then pass to the binary cross entropy loss. So this is sort of for those of you who know it, it's similar to RankNet, but where the pairs are constrained to have to be at least plausibly salient. And delta is chosen by cross validation. You can either choose it. Yeah.
You see, what is BCE loss?
Oh, the binary cross entropy loss. So it's what's the other? There's another term for it. It's the log loss. So it's like So what you would do is you would say you convert the score difference to a probability, and then you take the pair and suppose it's the first one should be ranked higher. You label that +1, and if it's the opposite, you label it 0. And then your output probability is like a softmax or like a exponential function, or it's actually a logistic function because it's just 2 of the difference. And so what you look at the sort of, I think it's basically, it's like the Kullback-Leibler divergence from the ground truth, which is the binary label of the pair order and the probability you assign. Yeah, it's, go ahead.
Sorry, and you're only training on pairs of the samples that differ greater than delta.
Yes.
Okay.
Yeah. So the thinking is that if you split them out that way, you'll at least get one, by looking at all pairs, you'll see each thing more frequently, and also sort of learn to relatively order. And you sort of you could think of it as putting some sort of micro force between the ranking orders that reflects what we see, so that things should be higher, as opposed to just predicting. So the AAC is between 0 and 1, and if you just run a linear regression model, you can do okay on MSE by just predicting 0.5, right? So it gives you a good forcing function that way. Then when it comes time to predict a score of a new cell line, we just put it through the clone network in this case. Yeah.
So this distance is calculated for population or for individuals?
You're talking about the delta here? The delta is a fixed parameter, and it's a hyperparameter. So you go in and say, I'm going to only consider, you fix it a priori and then run the model and evaluate performance, and repeatedly do that for different values of delta, and the ones that give you the best one is the delta you pick. So it's tuned empirically. There's no sort of theoretical justification for how to get it.
You want to speak about personalized medicine. So where is the individual in this?
The individual is going to be, so this is when you train it. The individual comes in next, which is what's called an inference time in the machine learning literature. So here, if this vector is some new patient, really new cell line, and you would never go from cell lines to patient without a lot of real world caveats. You pass in the vector of expression, And after the network's been trained, what you get is a drug response score that should help you guide. So for this particular individual, represented by this vector, what's their drug response to this? What do I predict is their response to the drug that I'm considering? And then I can sort of say, so theoretically, right, I could build a bunch of these models, one for each drug that I'm considering, pass the patient in, and then choose the drug with the highest response score. So that's how you would get to personalized medicine. This is about what we're dealing with here is sort of a little bit upstream, which is how can you build a model off when you're developing biomarkers, often it's with the preclinical stuff like cell lines. And those are really noisy, but you have to be able to sort of build models off of that before you even try anything in a patient. And so what we're aiming to show here is that by ignoring noise in cell lines, you get a model that generalizes better. And that's something to keep in mind as people develop their models in cell lines or even biomarkers. Sort of a two-pronged approach of you should be nervous about taking the results of these screens too much on the face. And also training models should be aware of that noise. Does that make sense?
Does
that answer your question?
Well, it's a fair attempt, but since you are talking about noise, maybe you can go to the slide
this one?
Yeah, it's a beautiful slide.
Thank you.
But you went very fast. So it looks very symmetric, and I know that noise is a big issue in many troubles and many forms of noise. So maybe you can explain this again or better.
Sure. There are so there are multiple sources of noise, and this is just one particularly bad example of sort of we've pooled all the replicates from all these studies. So the symmetry is a bit, it's sort of confounded by the fact that we've pooled everything. But there are at least three kinds of noise I can name at present. And I'll talk about how they show up in the slide in a second. There's institutional noise, right? So in the sense that the way that we may do some genetic analysis or do a screen over at Princess Margaret likely will be different from how the machines they use and whatever they use at MIT, Stanford. After you get at a machine, you also have issues of sort of subsequent, like the machines have their own noise. So an example that my mental model is DNA sequencing. In classic short-range shotgun sequencing, you can have DNA and then make an error early. And then as you do PCR amplification, that same initial error gets blown up. So that's just a potential flaw in the way the assay is done. And then here, I didn't include the slide, and I probably should have. The way that these points are found is you take a drug and you take various concentrations of it. And you run this process at various concentrations. So it's not just one drug, one cell. Let me look at the red drug at usually a logarithmic, evenly spaced range of doses. And then I fit a dose response curve to that. And usually the results are averaged. But what can happen is due to these assay noises, assay noise, experiment noise, measurement noise, right? You'll miss. Right? Suppose I look at a particular concentration for a drug in one replicate, but the machine fails. So I'll have missing data. I'll have things randomly deleted. If you look at the curves, and I can try to find one after the talk and show you, they vary pretty wildly. So what this slide is showing you sort of each of these points summarizes a curve in that dose response landscape, and it could be very different. And it's sort of subject to they usually are fit to some sort of set of parameters and constrained to be sigmoid. But if the dose response is flat, you're going to have a bad fit, right? If it's just a straight line of points that you try to fit a sigmoid to, or things will be missing. And so what you have here is just sort of summary results of sort of layers and layers of issues that can come up. And the reason it ends up symmetrical here is because we pulled it. So I guess so to pull all this back to personalized, if you were to say, come to a clinic, supposing that I were an oncologist and you came to my clinic with your DNA, and I went and looked at a cell line screen and said, okay, like the simplest solution to anything comes like algorithmically is a lookup table, right? So what you might want to do is say, come into my clinic, I'm going to look up the cell lines that are most similar to yours. And this is a little bit of what I'm going to try to do later. And just recommend the drug that's best. The argument about this slide is that when you say best out of those cell line screens, you are actually working with data that really cannot be trusted. And so you want to sort of ignore and look at measurements that are well separated, because if they are well separated, it's more likely that you're dealing with biological reality than measurement noise. And so if you look at those and build it out, you can then experiment further and say, we've been a, usually we'll go from a cell line to say like a implanted in a mouse where there's more complexity. Our hope is that training a model on cell lines this way will make it more amenable to sort of more complicated model organisms. Does that make sense? Or is it? Okay. Yeah, I'll happily, I can revisit this question. I'm around. Sorry, it's too far. So yeah, we then pass it in, and we've trained it on the Broad screen, which is really two. It's because of fun MIT internal politics. There's two papers, the Cancer Cell Line Encyclopedia and the Cancer Therapeutics Response Portal. One has the expression, the other has the drug response, and you have to harmonize them. And then we evaluated on two completely different data sets, a Genentech screen and one done by the Sanger Institute. And we split it up by looking at both seen cell lines and unseen cell lines. I'm only going to give you some of the drugs. Look at 21 total. So, accusations of cherry picking will be hopefully dodged, but we'll see. So this is what 5-fluorouracil looks like when we look at the seen cell lines across both. And our three baselines here are, I guess, four. We have an elastic net and a random forest, two classic methods, a univariable, which is just the expression of the gene that has the most mutual information with drug response. And then the ground truth, because these are seen cell lines, there's overlap. And so what we're saying is, what if we had just kept the overlap? And the answer is sort of what we're finding here, right, is that the concordance is pretty low. Concordance of 0.5 is essentially a random predictor. So 6.3, 6.5 is not like great. But it is consistent, at least, with some of the noise. That if you're looking at overlap, you're finding out that there is going to be some measurement noise across these assays, especially as we're going, between institutions and between methodologies. What's fun, though, is if you look at the unseen cell lines, at least among Genentech, the two-layer neural net is much better. So in some cases, we're able to find, and obviously in GDSC, it fails. Everything fails. Similar things show up in Ufitinib, where, again, the neural net seems to outperform its baselines, and GDSC remains difficult. It's also true, like, there is a caveat to put here, which is that, and this is a mistake in the slide, not a mistake, a failure of the slides, that there should be data set sizes, because there is much more overlap with the Sanger than with Genentech. Genentech was designed to be sort of more minimally overlapping with existing ones and higher QC. So, like, essentially, Genentech, the GCSI screen was made, was conducted because people were finding that the other existing screens did not make any sense put together. And then, again, not to say that we always win. For Pictolisib, we get kind of creamed. But what's nice is that, at least sort of going through the results sort of slowly, in cases where there is some signal to pick up the model, pick up between cell line omics and output, which is, the test bed is unseen, right? We do seem to do significantly better than our baselines. But in cases where there is, it's not like we're ruining signal, we're finding it, but in cases where there really doesn't seem to be much signal, we're competitive with every other model, but nothing does particularly well. So let's stop and reflect. There's some signal, and when there is, ignoring noise seems to help. But in some cases, the ground truth, no model as well, including the ground truth, right? Like the ground truth is close to like pseudo-random. I can get it. No, you're fine. Sorry to post online if you just heard a large door sound.
Since I interrupted you anyways with the door, how dependent are these results on the delta value?
Fairly. So we've done some parameter sweeps, and it's I sort of two answers to the same question. One, when we cross-validate it, it always picks a delta that's positive. So it's never just choosing all pairs. Two, when we've done parameter sweeps, it is like relatively continuous, but it seems to be, it's very dependent on the layer, it's dependent on the drug and the cell line in a big way. In some cases it doesn't matter, in some cases it does. A thing we tried that ended up not working, and like a very starkly unilaterally reduced performance, was adding in a second parameter and just saying, if it's AAC is above this threshold, then we care about that too. So trying to push everything to the top. And that actually, like, we had these box plots that were delta and model performance, and it was, some cases it was like way up at like 0.8 concordance, but then if you add in that second parameter, which was tuned in a drug specific way, it would cut it in half. So it's not, it's like somewhat dependent, but it is more, we're picking up on measurement noise on a per drug basis in a way that I feel pretty good about. So think about what makes a good ranking, right? Usually you'd want them to be transitive, right? This seems sensical. But at least social choice theory says this doesn't really happen. This isn't realistic. So the Condorcet paradox says that for any sort of voting system, you can have majority rule and actually no one can be satisfied. So you can actually get empirically intransitive relations. So these sort of inconsistencies or cycles might be unavoidable, and maybe they're intrinsic to the data. And so at the risk of throwing the baby out with the bathwater, could we be losing something by ignoring noise? Could there be a reason that these replicates are a biological reason for that swappability? And sort of in a different way, this is what these dose response curves look like in GDSC for 5-fluorosil, for example. Permuting within the green region and within the red region are likely not going to cause too much of an issue, right? Because your swap, like concordance penalizes the whole list. But it would be nice to know, hey, at the top, how are we doing? How are we doing at the bottom? And can I swap the bottom two and not do anything? Because that'll, like, if I swap the bottom two, concordance-wise, I'll have lowered my performance. But realistically, and in terms of what we might want to get via biological insight, it doesn't make much of a difference. So can we look a little bit closer at the resulting rankings, and can we sort of maybe find these specific inconsistencies? So it's taking us to the final and sort of more speculative part. There is some code at the end, some results at the end, but this is sort of a open, sort of articulating a new direction, which is to take the Hodge rank procedure from, I think, almost 20 years ago now and apply it in a personalized medicine context. So at a high level view, we're going to try to look at the dual problem, or I said inverse, but I guess since it's the Field Institute, inverse problems means something's very specific to you folks, and my many apologies. So I'm going to look at the problem of ranking drugs based on the omics. And the idea is to sort of cast it as assigning scores to nodes in a graph, pairwise differences as edge flows, and then using what ends up being a sort of discrete Hodge decomposition to find triangular inconsistencies in that flow. This was, the original ranking algorithm was proposed in 2009, but no one has, aside from one paper that's come out recently, has applied it to biomedicine at all. And that is a shame because it's really wonderful, it's self-certifying, it's interpretable, and our proposed innovation is to try to make the procedure more personalized. So the idea, should this, science willing, this will be both it'll be certifiable and actually useful in the clinic. So the idea behind DeepSciNet was if we could order all the pairs properly, right, you can get a ranked list. And this is a classic, like total order implies pairwise comparisons and vice versa. So we could think about modeling these as continuous functions on a graph. So if you have two drugs that are in the screen, each node is a drug now, connected by an edge, you can look at a sort of relative preference, which is this edge flow y, which is going to be an alternating function on the edges. You can think about it in some ways like starting here, this vertex on the left, and going to the right, you sort of increase your net preference, or if you're an economist, like net utils, or in our case, sort of increase percentage of cells killed by the value of Yij. And the skew symmetry comes as a result of sort of wanting that to make sense, right? You shouldn't be able to sort of say, if I give you erlotinib instead of paclitaxel, I'll kill 20%. But if I go the other way, I'll only kill, it's logically what we want out of our ranking system. So at the risk of oversimplifying, I want to sort of think about some fake data here, where we have 4 drugs, 2 cell lines. And these are their AAC values, and the dashes indicate missing data, which is one of the main hallmarks of why this HodRank procedure is so nice. DeepSciNet can only look at pairs that both exist in the data. HodRank is designed explicitly to be able to handle missing data. It's either incomplete, which you might see here, because not every cell line screen is going to screen every drug, noisy, as we've talked about, and imbalanced. Certain cell lines are older and so will be more screened. Cell lines that have their genetics already done are likely to be more screened so that they don't have to, I don't want to be Princess Margaret have to resequence everything, although we do. And certain drugs we tested more because they are cheaper compounds to get. So how can we turn this into a graph in pairwise ranking as an edge flow? Let's look at just the first cell line. We're going to do this one at a time. Create each drug as a node. Add an edge if and only if they've been compared. And then there are many ways to do this, but the way that I choose to do it, and that it makes the most sense in this context, is to compute just the difference. So here, because drug 3 has an AAC of 0.1 and drug 4 is an AAC of I think this is a fun little arithmetic error. So going from drug 3 to drug 1, I've flipped my signs, my mistake. Point being, you could take it all and you aggregate it into an average flow and a sort of overall graph. What the discrete Helmholtz decomposition says, and I'm going to ignore the math of this because it's either me saying cochains and cohomology for 30 minutes or some linear algebra, and we can do the latter afterwards. But the takeaway is that you can take these pairwise edge flows, meaning the thing we've just averaged from our data, and decompose into 3 things. A globally consistent ranking score. So it means a score that is assigned to each node that is guaranteed to give you a full list that is not cyclical. Locally consistent, meaning orders that are not, if you look at a triangle, are not, you can't increase your score by walking on the triangle, but there may be sort of a larger tier, sort of global cycle that you could walk around and increase your value. So essentially you can think about that as like a certificate, the magnitude of that component has a residual that says, if I have a ranking and that residual is large, I probably shouldn't believe what my ranking says, because there probably is like the number of permutations that I get that give me a relatively similar quality is quite high. And the last thing you can get is a projection onto locally inconsistent rankings, meaning triangles in the graph that should be looked at as I can swap among these and not really change much. So what we're going to do is take our average network flow here and do orthogonal projections onto each of these components. So we're going to look at the drug, which will give us drug-specific scores, a measure of ranking quality, and a set of permutable triangles to look at. How do we personalize this? it's how we build this data set. So the idea is take a cell line or a patient in, look at the ones that are most similar to it. That gives us our data, which may be missing, noisy, et cetera. Run the procedure, and then output for that patient a set of drugs at the top that we think are worthwhile and the ones that might be worth permuting, or that can be permuted without changing your results. So to give you, to maybe ground in some intuition here for a second, where is it? I think I went by it. Yeah. So suppose that this is, so if you take if you make this kind of plot here for a cell line, and instead of the drugs being the points being cell lines, or now the points are drugs, you'll get something that looks very similar. And so the question becomes, what separates the drugs at the top from the drugs at the bottom? So this kind of coarse-grained look is important to maybe say, what's the mechanism of action behind a given drug? What's the reasoning behind what do these drugs have in common that are maybe not effective on the cell line? Are they targeting a given receptor? Are they targeting, or are they not? You know, it's a way of sort of chunking the list up more thoroughly. So I want to do a very simple example result. Just go through this at the end and then we'll finish. I looked at the cell model CVLC 1128. It's a Cellosaurus ID. It's a lung cancer. I constrained to 4 drugs for the sake of being able to plot it and discuss things and not have a slide that rolls onto the floor. So here's the ground truth AACs of this selling with these drugs in therapeutic in the Broad screen. I looked at the 2 and 5 nearest neighbors in both a pan cancer and among lung cancer cell lines, and then ran the Hodge rank procedure to get both a final ordering on the drugs and compute the curl component, the cyclical, sort of the triangles that are worth, like, potentially exchangeable, I guess. And these are the results. Highlighted in green are the things that are in order. So if I look at the 2 nearest neighbors among lung cancer tissue, I get the exact right ordering. And each approach sort of gives you some sort of, you get the top 2 are permutable and the bottom 3 and the bottom 2 are not. Interestingly, when we do the projection onto the curl component, it identifies those 3 as being exchangeable, which in some ways makes some sense because they're the only ones with positive AACs. So what's next? Scale up to larger sets of drugs on optimizing the number of neighbors, find failure modes, identify problem cases, and also look at other ways in which this could be applied. And the other thing that I think is most interesting is how do we build this nearest neighbor set? When are 2 cell lines actually similar? And how can we do that in a sort of nuanced, multi-omic way? It's important to me to acknowledge my lab, and I wouldn't be here without the kindness and generosity of my PI, Ben, there in the front, orange shirt. Thank you guys for your attention and time. Please pepper me with questions.
Thank you very much, James.
Pleasure.
Does anybody have any questions?
Hey. Must have been
I
successful.
have lots of questions, but
There was a question in the back.
See, how intensive is the training for these machine learning models?
Oh, it's not bad. It's we're not doing like LLM. It's not.
Yeah.
If it takes me a week to train this model on every drug, it's because I'm low in the priority queue on this cluster. Like training one of these models maybe takes half a day at most. And that's because and when I say half a day, I mean that to try to do 10-fold cross-validation on every possible hyperparameter value. To train for a fixed set of fixed set of hyperparameters, you can train on a Mac in 5 minutes or less.
can you go back to the construction of the graph? I got lost in
Sure.
I understood how you constructed your YIs. And then I got lost when you said you did something after that. So how do you go from, you've constructed these edges from your data. Now what do you do?
Great question. So the way that I do it, right? So there's the concrete answer is you look at each cell line, right? The way you build your final graph is you take all the drugs and put an edge between a pair of drugs if at least one cell line was experimented on both. And then the flow on that edge is a weighted average of the yi's that you compute for each cell line. So you sort of essentially, if you have for each, so like sign issues aside, right? You have this is your like graph for the first cell line. You have a similar one for the second one. You essentially compute the union graph and then average the flows across the edges. And then you have a sort of aggregated flow and sort of aggregate pairwise comparison graph that you can do analysis on. The other thing that's interesting, or I guess the thing that's the high level answer is, if you look at the original paper by Lim et al., or I think is it Lim? It might be Jang. The or the authors, they generalize this much higher. It's to the point of view, the way you construct the yi's can be done as like a difference in probabilities, arithmetic mean, geometric mean, look at the difference, the sign of the differences, etc. And then how you average it can either be, in this case, it's just a vanilla unweighted average. I mean, the weights are all unity. If you could have it be that the number of the weight that you give is the number of times, this is the thing we want to experiment, that number of times a cell line or a person made a particular comparison. So if a cell line, if a drug pair has been in multiple screens, instead of having it weight 1, we'd have it weight 3, for example. So that's sort of more well-founded.
Okay, but then so after you have the edges that have a flow weight on them, positive or negative, then what are you doing with the graph?
Am I allowed to move this board and use it?
Yes, please.
Awesome.
Yeah.
Sorry, online. Sorry that you had to hear the floor. Yeah, I got it. Yeah, so sorry to whoever was doing tropical geometry. Or is it tropical? I heard it said aloud. So the basic idea is, all right, so if you have your graph, the graph is just sort of more of a like it's a nice mental device. You don't actually need to use it. And you have your flow, right? Which is your, this can be represented as just some skew symmetric matrix, right? And the way that you then find the ranking initially is through a sum of squares minimization over skew symmetric x. Now, you heard me slip up and say curl earlier. And the reason that I did that is because obviously, if you think about like, I'm going to say Helmholtz decomposition, I'm probably using some like old school vector, grad div 0, etc. So the reason that this is globally cyclic is that we constrain X to be in some subspace of skew symmetric matrices. And sorry. Yeah, so what this is the set of X equal to negative X transpose such that Xij is equal to Sj minus Si. S is a function from the vertices to real numbers. So what you can think about this is like, you constrain your pairwise thing, your pairwise matrix, to be the discrete gradient of some potential function on the vertices. And then from this, essentially you take an adjoint, and then you can recover S by solving a least squares problem. So it's really just, I think it's actually like, if this is so I think I'll try to use their notation, but if this is your basic graph Laplacian, and this is, you have it's the incidence matrix. So it's what I'll call it the discrete gradient. You solve this, and it ends up being pretty computationally efficient. And that's how you can, this is like, let's actually get them on the slide. Solving this is how you get the leftmost projection. So you're essentially doing the normal equations to project onto that particular subspace. The locally consistent one is a similar thing, but it's a question of, you essentially have to solve it over triangles. And so it's a little bit, I mean, the computational limitation is that you then have to do this over, if the graph is really dense and large, then that becomes intractable. It's like, end of the 6 or end of the 9, sorry, to solve that in a typical way. And the reason that I say Hodge theory is that the last thing here is, you essentially have the way that it works, the way that the setup, and the reason why they appeal to topology at all is, these are scores, which are, zero simplex or vertex functions, alternating functions on edges, alternating functions on triangles. And if you think of the graph in terms of its like clique complex, then these become, whatever sort of co-boundary operators. Yeah, they choose an inner product and take adjoints. So that's why they say just by doing some, real like quotient space linear algebra and constructing you can get what is like the graph Helmholtzian, or like the discrete vector Laplacian, if you're so inclined. Because I'm a computer science guy, I'm much more comfortable in discrete spaces. I know you guys are diffie people, so I remain in awe. That looks something like, let me get this right. Delta 1 adjoint plus delta 0. And then essentially the locally consistent rankings are called harmonic, because it's what you're projecting is onto the kernel of this, which is solving the vector or the discrete higher order Laplace equation. So I feel like I've gone a little bit far astray, but to answer your initial question, you set up this flow, you think about the graph as a nice tool for like both visualization and grounding intuition, but really you're just solving a series of least squares or orthogonal projection problems that are pretty doable on modern machinery.
Great. And then at the end, after you do that, what do you get? Because now I've kind of forgotten.
Too.
Like deep dived.
Yeah. So what you get at the end is right. So at the end, let's say we have our graph again. I think I'm gonna get this right. Is that it? I think it's something.
That was it. Yeah.
Hell yeah. Step 1 is solve this min problem. And then because of how we constructed this, we have a solution, which we know x star ij is given by this formula. And so we can, up to an additive positive, whatever. Just invert this to get a score vector.
And this gives you the ranking?
That gives us our ranking.
Okay.
And because of how we constructed the subspaces, we can just sort of say, I is preferred to j if, si greater than or equal to sj. And because we've constrained it to be this way, if you were to look at a triangle and just do the sum around it, you're going to get back to 0. So this is you're not like, because how we set up the subspaces, you're, guaranteed no cycles. And so then you can either, you sort of have options here, because, we still have 2 subspaces left. You can choose which one you want to solve for. I tend to like the curl one because I think for our purposes, where the triangles are is a lot more interesting than like what, and just the scalar of how big the residual is for the harmonic component is more interesting. So 2, you'd solve a similar thing, sort of a min. It's like phi is in the image of that. I forget the exact detail. You minimize a similar, and then you get the result here is a triangular flow, which you can then, meaning it's a function on a triangle. But from the setup before, right, we have that this sort of undefined adjoint function takes triangle functions to edgewise. And so we then get our sort of triangular component via, rather than using star to mean both adjoint and optimum here, I'm sorry. Let me make it a hat. There we go. And so this is a skew symmetric matrix. This is a skew symmetric matrix. And then the harmonic component is just found by subtraction. So you can say, and this is the next step here, right? It's to take
I guess the question that my brain keeps going back to is,
you're asking me things, I'm just like writing symbols, and that's
yeah,
that's how
you're losing me.
Yeah,
You're losing me on this. I'm sorry.
no, you're fine. I think that's a me failing.
No, it's on me. But the question my brain keeps coming back to is, like, what does all of this mean in terms of the biology?
The biology needs to actually be, yeah, no, I get it. I get it. So the biology is then like, sadly here the thing is like the biology is like a follow-on, right? So suppose what we then would do is look at, this is why I'm trying to focus on the triangular parts, right? So suppose I give you a ranking, right? And I give you the residual on the ranking of the global ranking, and I can say that means this really isn't that good. Suppose I take all my tissues or all my cell lines, and I can say, or even from a clinical point of view, right? Suppose I have this in the clinic. I can say, these are the therapies that this AI model or this Hodge model thinks you should use, but the residual is really high, so I wouldn't trust it. It's self-certifying. On a second level, suppose I give you, hey, this is a good ranking. Let me highlight these triangles and pull out what are their mechanisms of action, right? So suppose this is like another, so if you were to look at, think about like screening for organoids, right? So do people know what an organoid is? Basic idea is you can grow patient tissues in vitro, but so that the 2D structure exists. And we have a thing over at the Princess Margaret, which is really cool. It's the living biobank, where you take a patient's tumor, grow the organoid in a petri dish, and then can experiment with a bunch of compounds on it. What you could do here is say, at the top of my list, this is my rank order, but I can swap the top 3, and I can swap the next 3 down and the next 3 down. So let me look at those. Oh, it turns out that they're all the same mechanism of action. So the goal here is to try to find, instead of just saying, this is where the explain it, this is where the this is the order, do this. It's be able to sort of look at these different items and then pass on to a biologist or a clinician and say, this is what we think. These are where we think. These are the treatment groups that are roughly equivalent. Let me, what do you think? So I mean, you raise an interesting and I think important and tough point, which is that a lot of these models, even Deep SciNet, is like not necessarily interpretable, right? And so building interpretable machine learning models is tough. So in my personal, genuine personal experience, we have a program at Princess Margaret called the N of 1, which is you have a patient who's at the end of, either has a really serious disease that's not responding to any treatment, and they can opt to say, send it to the people upstairs with the computers and see if you can pull something out. So I was dealing with a patient who had, sort of pretty serious metastasized disease, used our cell line derived signatures, came up with a ranked order, and showed it to their oncologist. And they're like, what is this? I would never do this. This one down here is interesting because I know that it inhibits this, and sometimes this happens in lung cancer. I can do this later. So there really is there's sort of a couple levels of gap between where's the actual biology to even going from model to actual biology to clinical practice is tough. But yeah, I take your point very seriously, which is and it's sort of where what I would love to do is when you're personalizing this, I think the right way to do it would be to see if you can come up with a biologically meaningful distance function and say, this is if instead of trying to rely on this to give you meaningful clusters of drugs, which you hope it would, hopefully you'd have a way of saying, these cell lines are similar in a biologically salient way. And so this should work better. But yeah, I think it's a good and tough point.
Great. Thank you so much, James.
Thank you.
I think we're good. Thank you.
Awesome.
I'll ask
Oh, chat.
my question.
No, it's just people chatting. Awesome. Thank you so much.
Thank you.
Of course.
So let's see.
Sure. Sure. I'm no longer sharing what we can talk about it.